Hello, everybody. I'm Slava Pestov, and I'm here to talk about the Factor programming language. Factor is an open source project that I've been working on for 5 years now. And first of all, to give credit where credit is due, Factor borrows from 3 other languages, Forth, Lisp, and Smalltalk. Forth places an emphasis on short definitions, code reuse, and metaprogramming. Lisp, of course, is famous for the code as data, macros, simple syntax, all of that. And Smalltalk has an interactive development environment, and Factor borrows features from all 3 of those. For this tech talk, I wanted to do something a little different than the talks I usually give about Factor. Instead of explaining all the language features in excruciating detail, I'm trying more to focus on examples. And of course, if something doesn't make sense, you can ask questions, but mostly this is about getting the big picture out rather than the details of the syntax and so on, just to keep things more interesting. First, I'll give an overview of what the language is all about, and then we'll dive right into looking at some real code. So Factor is a stack language, which means that functions, which we call words, they take inputs from an operand stack, and they push the results back on the stack. And at first, this may seem a bit strange, but during the course of the talk, you'll see all kinds of neat idioms and code examples where this works out really well. Factor supports functional programming, which for me, mostly this is about functions as first-class values and anonymous code blocks, which can be passed around. And we also do emphasize immutability, but we don't enforce it. There is still mutable states, so it's not purely functional, but it supports functional programming. Factor also supports object-oriented programming, and for me, this is mostly about runtime dispatch and polymorphism. Factor has a very rich library of data structures. We call them collections. And often you can use collections such as sequences and associations in Factor, where in other languages you would define new classes. And this is very nice sometimes because there are many words in the library for working on collections, which are very powerful. Finally, we have a very powerful input-output library, and a lot of the language features make it easy to interoperate with other languages, other programs, and stuff like that. For the cases where using the stack isn't so nice, we have named local variables, and this feature is implemented as a library, and that's just one example of a common theme in Factor where language functionality is implemented in the library, and this keeps the core very simple and easy to implement. And of course, the syntax can be extended because of that. The first example I'll show you is probably the least realistic program that you'll see in this talk, and it's the classical not quite hello world, but almost a simple factorial. And a factorial of an integer is just the product of all the integers which are less than or equal to that integer. So if you look at this code example, the first line just tells Factor that I'll be using a library called math.ranges, and this defines a data type for a range of integers. A colon begins a word definition, then the word name follows, and the thing in parentheses, that's called a stack comment or a stack effect declaration, and that just tells Factor how many values this word takes from the stack and how many values it pushes back. Then the definition follows, and the semicolon terminates the definition. If I click on the code example, then it is copied into the listener, and the listener is a tool where I can evaluate Factor code interactively. So now let me press enter, and the factorial definition has been evaluated. Okay, I can invoke factorial now, and I push 100 on the stack, then I execute the factorial word, and then I execute the dot word, and the dot word just prints the object at the top of the stack. So let me press enter, and this is a factorial of 100. It's a pretty large number. Now, let's go through this definition of factorial here in a little bit of detail, just so you get the idea of what the stack is all about. I'm going to press Control-W, which instead of evaluating the code immediately, it opens it in a tool called the walker, and the walker steps through the code. Okay, so I press S. Now it pushes 100 on the stack. Now I press I, and it enters the definition of factorial. I press S again, and it pushes 1 on the stack. And this word here, A comma B in square brackets, you can see it's a funny name for a word. And in Factor, we allow almost any characters to be used in word names. The idea is that you can kind of think of nice conventions, and you have freedom to write your code in whatever way you want. Now, this A comma B word constructs a range object from the number 1 and 100. And now we have a range on the stack. And finally, the product word takes any kind of abstract sequence of which a range is just one example, and it multiplies all the numbers in that sequence. And now we have the result on the stack, and the dot word prints it out. OK, so that's the single stepper, which shows you what's on the stack at each point. Now, the next example, it's a little bit more complicated. And this example uses our SMTP library to send an email. The first line here just sets a global variable with a default SMTP server. And this is the interesting part. I'm going to send it to my friend Doug, who's sitting in the audience there. This creates an email object. And I'll talk more about the object system in a little while. But basically, at this stage, all you need to know is that a word whose name is in angle brackets is a constructor word. And that's, again, that's just a naming convention for words that create objects. Then after we have an email on the stack, we push the list of recipients. This is an array which contains a string. And then we call this word. And this word stores that array in the slot name 2 of the email object. And then similarly, we set the source address, the subject, and the body. And then we send the email. And this word takes the email from the stack and sends it out.
The red periods at the end of each line, is that just...
That's just my text editor. I like to not have white space at the end of a line, so I have a feature that does that. OK, and I'm going to copy and paste this code into the listener. And in a few seconds, it should hopefully send the email. OK, well, I'll open a new window because it looks like it's taking a little while. Maybe the wireless here isn't so great. OK, now, before we can look at more examples, I have to talk about some language features. So as I said earlier, Factor supports functional programming. And essentially, code is data in Factor. Using this syntax with square brackets, you can surround any piece of code. And what that does is instead of executing it immediately, it pushes it on the stack as a single object. And we call these quotations. And they're similar to lambdas or code blocks in other languages. Words that take quotations as input, we call them combinators. Let me see if the email got sent. No, it's... Oh, OK. It worked earlier today. Yeah, a member of the audience just said that Google blocks port 25.
I don't know if they do, but I suspect.
OK. Yeah, here we go. It timed out. Never mind about that. If port 25 was not blocked, then the email would have been sent. OK, back to this. So words that take quotations input are called combinators. And in Factor, we don't have any hard-coded control structures in the syntax, and all control flow is done using combinators. Here I have 3 examples. The first example is a conditional. Let me click on that, transport it in the listener. The keyword here is if. Now, the if combinator, I can press Control-Shift-H to look at the documentation. This combinator takes a Boolean and a pair of quotations on the stack. And depending on whether the Boolean is true or false, it executes one of the 2 quotations. So this is how you do conditional execution in Factor. And in this code example, we start with 10 on the stack. Then we duplicate it. We check if it's negative. And of course, 10 is not negative. So now this is going to be false. And the if combinator will execute the false branch, which adds 1 to the stack. And finally, dot prints it out. So we should see 11. And that's what happens. The second example, we use the times combinator. And this is another control structure. It takes an integer and a quotation, and it executes a quotation that many number of times. So this code example should print a little message 10 times. There you go. This example, it's more complicated than the others, so let's take a look at it before we execute it. First of all, we have an array of strings, tomato, orange, banana. And then using the each combinator, we iterate through the strings, and we convert them all to uppercase, and we print them to a file. So how does this work? Well, the with file writer combinator, it opens a file, it calls a quotation, and then it closes a file. And this is how we do all input and output in Factor using combinators like this. And it's a lot more robust than the typical approach found in Java, for example, where you have to open a stream and then close it manually, because here there's no chance of a resource leak. Even if the quotation throws an exception, the with file writer combinator will always close the stream. And we have combinators like that for all kinds of operations on files and sockets and so on. The using line here, that just brings in a couple of libraries that we need for converting a string to uppercase and ASCII encoding. So let me execute that. And now the file should have been created. Oops. There you go. OK. So these are 3 little examples where we're using combinators as opposed to hard-coded control structures that other languages have. Now I'll talk about the object system. There are many different ways of defining what object orientation really is, but as far as I'm concerned, there are 3 key ideas: is encapsulation, polymorphism, and inheritance. In Factor, encapsulation is handled by a different set of language features. This is called the vocabulary system, where words are organized into vocabularies. And the object system doesn't enforce any encapsulation. The vocabulary system does. However, the object system does implement polymorphism and inheritance. And the Java, Smalltalk, Python, Ruby, Objective-C, their approach to polymorphism is that you have methods inside classes. And they use this metaphor of sending a message to an object, where you invoke a method on an object, and the object decides what to do with this message, and it acts on it. And here's an example where I have, this is just pseudocode in some kind of Java-like language, where I have 2 classes with instance variables and methods inside those classes. And I can send an area message to a rectangle, and it tells me what its area is. Or I can send an area message to a circle, and it tells me what the area is. Functional languages like ML, they take a different approach. And they use something that's called algebraic data types. And the approach there is that instead of having each data type define its operations, you define operations on the data types. So I define a shape, which is either a rectangle or a circle, and then I say the area of a shape is this if it's a rectangle, or it's this if it's a circle. And the perimeter, similarly, we switch on the type, and we do different things depending on the type. And both of these approaches have problems because with the message passing, Smalltalk style object orientation, it's hard to add new operations to existing types. So for example, if I want to add a draw method to rectangles and circles, unless I have access to the source code, some languages will give me a feature like open classes, which is quite a hack. But if you don't have that type of feature, then you're out of luck. But the second approach, that has problems too, because with this code example, if I define a new type of shape, such as a triangle, then I'd have to go back to the original source code where area and perimeter are defined and add a new case to these type switches. And neither approach appealed to me. However, Common Lisp did have a solution to this, and it's really quite nice. So what Common Lisp does and what Factor does is that we decouple methods from classes completely. A class, it does not have behavior, it is just state. And user-defined classes which hold named values are called tuples in Factor. There are other types of classes too, and I'll mention a couple of them later on, but tuples are the most fundamental type of class. So here I define two tuple classes, rectangles and circles. Rectangles have a width and a height, and circles have a radius. And the way this declaration is written here, it means that the width, the height, and the radius can be any data type. Factor also supports declaring the types of these slots, but I won't talk about that in this presentation because it's a more advanced feature. So now we have these two data types. Well, what can we do with them? You can create new instances for sure. So to create a new instance of a class, there are two fundamental words that are used. There's new and there's boa. If I say rectangle new, then I get a rectangle object on the stack where all the slots are set to F. And F, it's like Factor's null value or empty absence of something. Okay? If I say rectangle boa, then, well, boa stands for by order of arguments, so you can call it a boa constructor, and it fills in the slots from the stack. Okay? So with rectangle boa, I have to put the width and the height on the stack, and now I have a rectangle with these slots already filled in. Well, what if I want to change the width of a rectangle? You do something similar to the email example where you call a word with this name, the two arrows and then width. And now I've changed the width, or I can change the height. Okay, and if you create a rectangle with new, then you pretty much have to fill in the width and the height.
Let's say you've created a structure like this and have a large program using it. Later on, somebody wants to do some maintenance on the code and add a new field. How do you find all the places which need to be changed?
Okay, so the question was that if you're using boa constructors and then later on you redefine the tuple class to add a new field, how do you find all the places where you have to update the code and potentially add a new stack parameter? Well, you can certainly ask the system for usages of that class. And if you actually have words that call boa on them, we don't have words, we've just been calling boa in the listener, it will tell you. But mostly, if you have a class with a lot of slots and a lot of them are optional, then you use new and you fill them in using these setter words. You would use boa for very small tuples. For example, if you have a data type for points with an X and a Y slot, or you have a data type for colors with red, green, blue, it's not likely that you'll be adding a new slot. And calling the setters by hand will be more verbose than just having the values on the stack. Yes? Can you repeat the question, sorry?
Why is F in the rectangle?
Oh, okay. Well, the question was, what are these Fs here? Let me clear the stack. When I say rectangle new, then it makes a new rectangle object, and it doesn't take anything from the stack. Oh, Y3? Okay, that's just a funny bit of syntax where if the first F can be something else, and then you can look it up in the reference documentation if you're interested. Okay, but usually we encapsulate constructors in words. So you don't ever call new and boa unless it's inside a constructor word. And like I said before, the naming convention for constructor words, it has these angle brackets around the word name. So here I've defined two words, rectangle constructor and circle constructor. And they basically do what I was doing here, where you put the width and the height on the stack, and then you can create a rectangle, or you put a radius on the stack, and you can create a circle. And once you've defined constructor words, it's easier to find, if you use them in a disciplined manner, it's easier to find all the locations which you might need to change if you add a slot. So that's another answer for an earlier question there. Okay, well, that's all very well, but so we can create these objects and get the slots, set the slots, but what can we do with them other than that? Factor has this thing called a generic word, and a generic word is a word whose behavior depends on the type on the stack. Generic words are defined by saying generic colon, then a name, and then a stack effect, but there's no body, because you'll have multiple bodies depending on the type. Okay, and a method in Factor, it associates a class and a generic word with a specific behavior. But methods, they don't live inside classes in the same way that they do in Java or Python. So here I'm going to define two methods on the area generic word. And the first one is specialized on the rectangle class. The second one is specialized on the circle class. And the definition might look kind of funny, so I'll talk about it a little bit. See, the area generic word, it takes a shape on the stack, and it outputs the area of that shape. The area of a rectangle is the width multiplied by the height. So if we have a rectangle on the stack, we have to get the width and the height, and then we multiply them. To get the width and the height, we use the by combinator. And the by combinator in Factor, it takes an object and two quotations, and it applies each quotation to the object. In this case, the first quotation extracts the width, the second quotation extracts the height, and now that we have the width and the height on the stack, we multiply them. And the way you read this code is get the width, get the height, multiply them. And for the circle, it's simpler. You just get the radius, you square it, and the SQ word just takes a number and multiplies it by itself. And then you have to multiply that by pi. Okay, pi r squared is a formula for the area of a circle. And now that we've defined these methods, we can compute the areas of rectangles and circles.
What would happen if you get the stack discipline wrong in the rectangle code?
Okay, so the question was, what happens if you get the stack discipline wrong in the rectangle code? It depends on whether the code is in a source file or you're entering in a listener. If you enter in a listener, then you pretty much won't find out until you run the code. If you enter in a source file, you get a compile error. So the compiler checks your stack usage, and if anything is wrong, then you get a compile time error. Okay? All right, moving along now. Let's define a new operation on existing data types. So here we have a generic word called perimeter, which takes a shape and outputs a number, and it has two methods, a rectangle method and a circle method. The perimeter of a rectangle, we take the width and the height, we add them, and then we multiply that by 2. The perimeter of a circle is the radius times 2 times pi. And now we can compute perimeters of rectangles and circles. Okay, but what about defining a new data type and implementing existing operations on it? Well, you can do that too using this model. Here I have a triangle data type with a slot for the base and a slot for the height. So this is just a right triangle where the angle is 90 degrees. Then we have a constructor word as usual, and we put a method on the area generic word that we defined earlier, which multiplies the base by the height and divides that by 2. So let's try that out. Okay, that looks correct. And again, this is another method for the perimeter generic word. The perimeter of a triangle is a little bit trickier. You have to compute the diagonal line, the hypotenuse, and I guess a picture would have helped. But basically, the hypotenuse is the square of each side. You add it together, and then you take the square root. Okay, and once you have the hypotenuse word, then you get the base, you get the height. Now they're both on the stack. And what 2by does is it's like by, except now it takes two objects and two quotations and applies each quotation to both objects, okay? So here we add the base and the height, and here we compute the hypotenuse, and finally we add those two together. So that's a little fun piece of code. And there's your perimeter, okay? And you get a decimal number because there's a square root in there. Okay, so using generic words and methods, you can define new operations over existing types, or you can define a new data type with existing operations. And that gives you more flexibility than the message passing approach or the algebraic data type approach. And the next feature I'll talk about is, it's called Mixin Classes. And to motivate Mixin Classes, let's look at this. Every class you define has a word which tells you if the object at the top of the stack is an instance of that class. And here we're checking if a rectangle is a rectangle. Of course, this is true. But a circle, it's not a rectangle. But what if we want to have a word which tells us if something is a shape in the general sense? Well, you could define a word which checks if it's a rectangle or a circle, but that's not exactly what you want, because what if someone comes along and defines a triangle data type with methods on area and perimeter, and then your word won't work? It's not general enough. So what we do is we define a Mixin class called shape, and we say that rectangles are shapes, circles are shapes, and triangles are also shapes. And once we've done that, we can ask a circle if it's a shape, and it says true. However, a floating point number, it's not a shape, because we didn't declare it an instance of the Mixin. Now, the nice thing about Mixins is we can define methods on Mixin classes. So here's a generic word called tell me, and if you give it a shape, it prints the area of the shape using the dot word that we looked at earlier. If you give it an integer, it prints a message telling you whether it's even or odd. So if you pass a circle, you get the area. If you pass a rectangle, you get the area of that. And if you pass an integer, it just tells you that it's odd. And this integer class here, it's not a tuple class that we defined. It's called a built-in class. And Factor has built-in classes for integers, arrays, strings, and all the other stuff that you'd expect to find in a language. And you can add methods on those. So you're not limited to working with tuple classes. You can extend the integer class with custom methods, or the string class with custom methods. And back to our shape example, now that we have these two generic words and we have that shape mixin, anyone can come along and define a new tuple class for shapes, make it an instance of the mixin, give it these two methods, and then they can pass it to a word such as this. Okay, so a mixin lets you inherit methods, but not state. The object system has other features. You can actually inherit state as well by subclassing tuple classes. You can declare types. You can make slots read-only. And there's more types of classes than just tuple classes, built-in classes, and mixin classes. We have this one feature, for example, called Predicate Classes, where you can say, define the class of all strings with length equal to 5, and then you can put a method on that. And the method will only be called if the string has a length of 5. And the object system is implemented in Factor, and it's only 2,000 lines of code. And that's a recurring theme where large chunks of functionality are not part of the core language. They're just in the library. And this makes the core smaller and simpler. OK, and
What happens if more than one method is applicable?
the question was, what happens if more than one method is applicable? Yes, that can come up when you have multiple inheritance of mixins. And the answer is that we have a linearization algorithm which determines an order for methods. And you can ask a generic word for the precise linearization of its methods if you're ever confused about the applicable method. So it's not ambiguous. OK, now functional programming and object-oriented programming, they both come together in Factor's collections library. We have many types of collections. The one that's most commonly used is sequences. And a sequence is a linearly ordered set of elements. And this includes arrays, which are just fixed length sequences of objects, vectors, which are resizable arrays, and strings. Factor also supports associative mappings, and the most common example there is a hash table. And there are others like red-black trees, which are more obscure. And we have a lot more collections, decks, heaps, disjoint sets. But I won't talk about them except for mentioning that if you look in the vocabulary browser for the vocabularies which are tagged with the collections tag, then you'll get a list of vocabularies which are either implementations of collections or algorithms on collections. OK, let's talk about sequences. So sequences, there's this thing called a sequence protocol, which is a set of generic words which, for example, get the length of a sequence, set the length of a sequence for resizable sequences, get elements, and set elements. And anybody can define their own type of sequence, which has methods on these generic words. And as soon as you do that, you have all these combinators you can use. And you can iterate over a sequence. You can map over a sequence. You can remove elements which do not satisfy a certain predicate. And you also have utility words, which you can use. And the way that works is that these combinators and utility words, they simply call the generic words on the object that you pass in. And as long as that object is any data type which implements methods on these generic words, it's going to work. So here you have functional programming and object-oriented programming coming together, because iterating over a sequence with a combinator, that's a very functional idiom, where you have a sequence of numbers and I add 3 to each number and I map over it. But in Factor, this is actually invoking methods under the hood, so you can define a new sequence type. And here's an example that we're going to look at. It implements a solution to the bin packing problem, where you have m objects and n bins. And we want to distribute these objects as evenly as possible, but m might not divide into n. OK, so here's an example. We have 20 objects and 13 bins. And what the algorithm does is it puts 2 in the first bin, 1 in the second bin, 2 in the third bin, and so on. So let's look at how this is implemented. OK, and this is a typical Factor source file where you have 1, 2, 3, 4, 5 word definitions, and each one is just a one-liner that calls a bunch of other words. OK, there's a lot of code reuse going on here, and it's all very concise. And mostly we rely on sequence words to solve our problem. So the first word, percentages, it takes a number, and then it gives you a sequence of numbers from between 0 and 1, such that they're evenly distributed between 0 and 1, and there's 13 of them. OK? The second word is called steps. It takes 2 numbers, and here it gives you a sequence between 0 and the first number with the number of elements, and it's evenly distributed. So 2013 steps. Okay, here you have numbers between 0 and 20, and there's 13 of them, and they're evenly distributed. And these two words, the way they're implemented is the first one makes a range object and divides each element by n. The second one uses the first one and multiplies each element by m. Okay, and these are all sequence words which are combined in an interesting way, and there's no explicit looping here or iteration. The third word, called rounded, it just rounds each element of a sequence up to the nearest integer. So let's apply that to the output of the steps word. Okay, now you have just integers. And finally, the differences word takes a sequence and subtracts each element from the next one. And we've solved the bin backing problem. And we can, for example, step through the differences word and see what it does. So let's put the result of rounded on the stack, write differences, and press Control W. I press Control I to step inside. The first thing it does is it duplicates the sequence. Then it prefixes it with 0. And then it calls this word, which subtracts one sequence from another component-wise. And there's your result. Okay? And the interesting thing about this program is it processes your data in lots of little steps. There's no big loop or anything. And you can step through it. And even if you don't understand what a word like this means, you can look it up in the help. So as I mentioned earlier, this word takes a sequence of numbers and divides each element by another number. Okay? So this is an example that uses sequences. It's pretty complicated, but it solves an interesting problem. Now I'll talk a bit about strings. These days, ASCII, it's really not sufficient for what people want to do with computers, so most languages support Unicode instead. And in Unicode, each character is 21 bits, okay? In Java, for example, they use 16-bit characters, and that's a really bad design decision because they end up having to encode certain characters as 2 bits, 2 bytes. So you really need more than 16 bits, and Factor supports the complete Unicode standard. But the implementation is quite clever because if you dedicate 21 bits to every character, you'll be wasting a lot of memory for the common case of ASCII strings. So what we do internally is that a string is an ASCII string unless it has characters greater than 127. And as soon as it does, another vector is allocated of 16-bit values where each value contains the remaining bits from each character. Okay? And all of our string operations are Unicode aware. For example, case conversion, there's a German character where the uppercase variant of it is actually 2 characters, and we support that correctly. And we also support character classes and sorting and so on in a Unicode-aware way. So our strings are sequences, but they're quite a complicated implementation of sequences. But operating system input and output deals with bytes. So for a language like Factor, where strings are Unicode internally, you have to deal with encoding and decoding. And we support all the common encodings, such as ASCII, UTF-8, even the old IBM mainframe EPCODIC encoding. And the way this is implemented is that words that perform I/O, they take encoding symbols as input. For example, here, I'm opening a text file for reading, and I read a single line, and I do it with a UTF-8 encoding. I don't think the file exists, so I'm going to create it first. Hello world. Let's see, document.txt. And let me put a funny character here. There we go, a copyright sign. And I'll make it a UTF-8 file. It's already UTF-8. Save the file. And now when I read it in, there's a string with a copyright sign in it, okay? And of course, we also support binary input and output. And if using binary input and output, then instead of string objects, you get byte arrays. So we separate the two, which is quite important when you do this type of thing. Yes?
The with file reader, this is, I guess, kind of, the with file reader changes the definition of readline, or it seems to change what readline and print do. Like it changes.
Okay, the question was that with file reader appears to change the behavior of readline, and in the earlier code we had here with file writer appears to change the behavior of print, and that's exactly what's happening. Factor supports a feature called dynamic scope, which I wasn't going to talk about in this presentation. And basically with dynamic scope, you can define a variable whose value can be set, not lexically, but dynamically, meaning that you can redefine the variable, and then all callers of all words that you call see the new value, okay? So that's what with file reader does. It redefines the input stream variable, and then any words that the quotation calls, they see the new value of the input stream variable, and they read from that input stream, okay? I think the new buzzword name for that is context-oriented programming, but it's really just called dynamic scope, and it's been around since the 60s. But not many languages have it. Okay, so that's enough about sequences. Associative mappings is a similar situation. There's a protocol with generic words that you can define methods on, and of course, hash tables and other built-in types, they already have methods on these generic words. And then there are combinators and utility words, and you get those for free. So you can define a new type of hash table with a different collision strategy, for example, and you get all the functionality for free. Okay, the next feature I'll talk about is named local variables and lexical scope. And most of the time, Factor is very nice to program in, but sometimes there's no good solution to solving a problem on the stack. Or maybe you're just porting existing code and you don't want to rethink it in the Factor style. You just want to do it quick and dirty. And for this situation, we support named parameters, named local values, which are very similar to most other programming languages. And again, we can implement this in Factor as an embedded language, as a syntax extension. And our implementation of lexical scope is influenced by Scheme and Lisp. And instead of using colon, you use colon to define words of named parameters. And you can establish new bindings of let. And you can also have quotations of named inputs using this type of syntax, where you have a list of named values, and then you can refer to them in the body. And this supports full closure semantics, so you can return a closure from a function, pass it around. It also supports mutable bindings, and a lot of languages, they get the subtleties of mutable bindings wrong. For example, in Python, you cannot assign to an outer scope without extra work, but in Ruby, every function is just one single scope. So even if you assign inside a block, it will set the value in the outer scope. And that's kind of ironic because those languages have local variables as a built-in feature, but in Factor, they're just a library and we can still manage to do it correctly. And I'll show two examples. The first example is the quadratic formula. And the quadratic formula, it's kind of tricky because you have three values and then you have to compute different stuff. using those values. And just keeping everything on the stack can be a bit complicated. But if you use some name parameters, then it's very simple. So first we define a word called plus minus, which uses this combinator that I talked about earlier, which takes two values and two quotations and applies the quotations to both values. And plus minus adds the two values, and then it subtracts the two values and leaves both in the stack. And incidentally, this is a nice example of multiple return values with stack programming. And multiple return values are very easy to work with in a stack language. There's no packing and unpacking into tuples, for example, if you just want to return two values. This word here, it uses colon, and this means that these parameters are not just annotations for the programmer, they're actually semantic names, and we refer to the names in the body. And when you refer to a name like that, it's pushed on the stack. And this word here, again, it has name parameters, and it returns two values, and those are the two solutions to your quadratic equation. So this is just a little math formula example that uses locals. The next example uses lexical closures. And there's only one word here, and there's no inputs. It just returns one quotation as an output. And what it does is it defines a variable called x, whose initial value is 0, and the exclamation mark means that the variable is immutable, so you can change it. And then it pushes a quotation on the stack, but the interesting thing is that the quotation refers to the variable x, and it even changes it. And what it does is it gets the value of x. This should really be plus. It adds 1, and then it stores it back in the lexical variable. So let's see what happens when we call that word. Closures example. So let's call the counter word, and now it pushes this quotation on the stack, and every time I call the quotation, it's going to I made that change, but I forgot to reload it. Sorry about that. Okay, every time we call the quotation that it returns, it increments the variable x. But if I call it again, then I get a new closure, which has its own value of x, which is independent of the previous value of x. Okay, and some languages have trouble with closures of this form, for example, but it's very easy in Factor. As I said already, locals are just a Factorial library with 477 lines of code, and they use compile-time metaprogramming, so there's no performance penalty whether you decide to use locals or the stack. So it comes down to a matter of coding style, and very often using the stack is more concise and easier to refactor and so on. And in our basic library, there's only 59 words that use name parameters, but sometimes you do need to use them, and it's nice that we didn't have to add this feature to the core language. We just have a library that does it. Okay, now I'll talk a bit about the parser. You've seen this before already, where I can input an array just by using this curly bracket syntax, and of course I can input quotations using square brackets. And all data types in Factor have a literal syntax. Hash tables, for example. Here's a hash table with 2 keys and 2 values. And this is very nice for data-driven code, where instead of writing a big switch statement like you would in Java, for example, you can just put a hash table in the middle of your definition. Or you can also use Factor source files for configuration in your application. You don't have to write a separate configuration parser or use XML and then there's marshalling and unmarshalling of the data. You just load a Factor source file, which itself can contain lists and hash tables and stuff like that. But even more importantly, libraries can extend the parser with what is called parsing words. And the example I'll show you is the URLs library. It defines a data type for URLs, and a URL has several components. There's a protocol, hostname, port number, query parameters, and this library parses URLs. It can manipulate URLs, and it can convert them back into strings, but also extends the syntax of the language, so you can have a URL in the middle of your program. So I can evaluate this and push it on the stack, and the stack display now tells me there's a URL there. And this differs from a string in that the URL has been parsed and it has these component parts. Okay, so there's a query with ID 81. So that's an example of a library which extends a syntax. The core language doesn't have a notion of URLs. Of course, that would be silly. Now, another example where parsing words are useful is for getting rid of boilerplate. So here's a silly little Fibonacci sequence function. And the Fibonacci sequence, every element is a sum of the previous two elements, and the first two elements are 0 and 1. Okay? But this implementation is very slow. For example, if I do 34 Fibonacci, then that takes half a second, but it's only the 34th element. Like, what if you want element 1000 or something? And this is because if you profile it, I press Control R to profile it, it calls itself like a billion times or something, or no, 18 million times. Because every time you call Fibonacci, it calls itself twice, and each one of those calls itself twice, and it does this until it reaches 0. And it would be a lot faster if it didn't have to recompute all these values redundantly. And we can use a library called Memorization for that. And the idea behind Memorization is that before you actually perform your expensive computation, you check if you already saved the result in a hash table. And if you don't, you do the computation, and then you save it in the hash table. And this pattern comes up again and again in all kinds of programs. But in Factor, it's very easy to use this pattern because all you do is you change colon to memo colon, and as soon as you do that, then Fibonacci becomes a lot faster. Okay, 0 milliseconds. Because once it computes Fibonacci 34, it computes 33, and that computes 32, but then after it returns, next time it computes Fibonacci 32, it's already been computed. It's in the hash table. And all we had to do is change one token. We used memo colon instead of colon, and memo colon is a parsing word defined in a library. Now, this is similar to decorators in Python, I believe, but it's a bit more general because the parsing word can really do anything at once. And we use memorization all over the place instead of maintaining explicit hash tables for caches and so on. It's a lot nicer than writing all that code out by hand every time. Okay, so as I said, memo is just a library word, but so is colon. This colon syntax that we've been using to define words all along, there's nothing special about it. It's just a function in the library, and you can even look at its definition. It calls two other words. And Factor's parser is written in Factor, and all the syntax that you've been seeing in this presentation is just library functionality. For example, square bracket, that's not part of the language grammar. When I say hello world to uppercase map, then these curly brackets and these square brackets, they're not inherently part of the language. They're just library functions which happen to extend the parser to construct quotations, arrays. Even the quotation mark word here, the quote, that's a parsing word which creates a string for you. But of course, the question is, if if colon is a library word, then how can you use it to define itself? Like here, I'm saying colon, colon, and then giving the definition. The answer is that Factor basically compiles the parser to an intermediate form, and then you have to do this using an existing instance of Factor. The first version of Factor was written in Java, and then I used that Java version to re-implement Factor in itself. So now you use Factor to compile itself. In the same way that GCC is written in C and not assembly, for example, and you need another installation of GCC before you can compile GCC. This is called meta-circularity. And it's nice because I'd rather write the parser and the object system and everything else in Factor than write it in C, because Factor is higher level. Okay, so the parsing words I've shown you so far have been very simple. They either implement literal syntax for data types, or they just decorate a word with additional functionality, such as Memo colon does. But some parsing words are more complicated, and they embed entire languages with different semantics inside Factor. For example, parsing expression grammars is a library that we have which allows you to specify a parser for your own language declaratively and embed it in your Factor program. And using this, you can parse strings, and it's much nicer than writing a parser by hand. The example I'll use is a Factor implementation of Printf. And if you've programmed in C, then you're all familiar with Printf. The idea is that you have a string, and you pass it to Printf, and it prints a string, but it also interprets certain character sequences in the string in a special way. For example, if you have %s, then it splices another string there instead of printing out %s. Okay, so let's look at this thing here. EBNF colon, that's a parsing word which delimits a declarative grammar. Okay? And the declarative grammar roughly says that a string formatting directive is %s, and the action to take is to write the top of the stack when you see %s. A literal is one or more characters that are not equal to %. And the action to take there is you convert the literal to a string, and you splice it into an existing quotation, which writes that literal. And a printf format directive is a sequence of 0 or more strings or literals. Okay? So let's test out this EBNF word, parse printf. Okay, so it parsed our printf format string, and it gave us a sequence of quotations. But what we really want to do is get one quotation that just does the effect of all of these in order. And I can join them together because quotations are just sequences. So the result of parsing this format string is this quotation, and you can see that they both do the same thing, where if in C you pass hello, comma, %s, Newline to printf, then it's just going to write hello, then it's going to write a parameter string, and then it's going to write a Newline. Okay, and once you've defined a parser like that, you can make a macro called printf, and a macro, it's something that it runs at compile time. And that's what we want for printf, because the format string is not going to change. The parameters are going to change. So we parse the format string at compile time, and we join the quotations together as I did in the listener. And then you have a printf word. So let's try it out. Let me clear the stack because I have these ridiculous Fibonacci numbers there. I'll push a parameter on the stack, and I'll say hello %s printf, and it says hello Google. Okay? And the interesting thing about this implementation of printf is, first of all, we didn't have to write a parser for the format string by hand. And the second thing is that it expands into factor code at compile time, so there's no performance penalty to using printf in your factor program instead of just writing the code out by hand. And for such a simple syntax where the only special thing is %s, it's probably not worth using pegs. But where pegs shine is being able to extend your declarative parser very easily. For example, what if we want to support %d as a format directive to print a number? We can do that very easily. Here I'm saying when you see %d, the action to take is to convert the top of the stack to a string and then write it out. So if you have a number on the stack and you say number to string write, it's just going to write the number out. And now I just need to add this as one of the cases in the format string syntax. And here's another nice factor feature. When I change a source file that I've loaded previously, all I have to do is press F2, and factor detects that that file has changed along with any other files that have changed, and it reloads it. And now we can test it out. So 42, Googlers. Hello, Googlers. My favorite number is 42. OK. So pegs are a very nice factor library which extends the factor syntax to allow you to specify declarative grammars. And there are some extremely complicated peg parsers that we have that you really do not want to write out by hand. For example, we have a JavaScript parser that uses pegs. And as anyone who's written a JavaScript parser by hand knows, I haven't, but I'm sure it must be very tricky compared to just specifying the grammar declaratively. OK, so that's pegs. Oh, I had two examples here that I was supposed to show you instead of the 42 stuff, but it's basically the same thing.
How would you define, how would you abstract over the printf function? So I want to pass just printf to something. Can you do that? Can you define printf as
yeah, well, printf. OK, so the question was, how do I pass printf around as a first-class value? Unlike Lisp, where there are some limitations as to what you can do with macros, and you cannot pass them around as parameters, in Factor, that's not a problem. So I have a number on the stack, and I have an array with 2 format strings in it, and then I map over it with printf, and the width tells me that to pass the 5 on each iteration. Sorry, I'll use each instead of map. Then it works. Like, I have this quotation here that contains printf, and the problem with this type of code is that it's a little bit slower than something like this, because here the string, if you provide the format string as a literal, then the compiler will expand printf at compile time. But if you don't, it will still work. It will just have to parse these format strings every time it iterates through the array. So there's no problem there. It's just more of a matter of performance versus being dynamic.
So the compiler doesn't always check the stack signature?
No, it doesn't always check the stack signature. And it depends. Like, for some types of code, it cannot infer the stack signature if the code is too dynamic. OK, so I mentioned earlier that Factor has a very powerful input-output library. And let's see, we're sort of running out of time. So I'm not gonna, I was gonna give examples for all of these, but I'll just move on. Now, I'll give an example of the io.monitors library, which is really quite nice. And I haven't seen many languages which implement this functionality in a cross-platform way. And the functionality is monitoring the file system for changes without polling the modification date of the file. So let's look at this program first. The last two lines are the most interesting. We create a monitor object on the /tmp directory, and t, true, tells it to monitor subdirectories recursively. And then we do this forever. And what we do is we wait for the next change to come in. And this word takes a monitor and outputs the path name that changed and some kind of descriptor explaining what changed. And the forever word, it's not part of the library, but I define it here. And I define it using another word called loop. Loop takes a quotation which outputs a Boolean, and it continues looping as long as the quotation outputs true. And what forever does is it makes it so that the quotation always returns t by just saying call the quotation, then push t, and then pass that to loop. So let's try out this code example. And now when I create something under TMP, I get a message in Factor saying that this changed. Okay. And this uses platform-specific APIs, but we abstract over those APIs and give you a cross-platform interface to this functionality. And it's a very nice feature. It's very useful in a lot of ways. Like the F2 command that checks for file modification in your source tree, that uses monitors. And it's very fast because instead of having to look at every file and compare the modification date, it just sits around in the background with a monitor. That's just one example of a cross-platform I/O feature that Factor provides that many other languages do not have, and you have to roll it yourself or tie yourself to platform-specific functionality. Here's another example. This is a time server where every time a client connects, it sends the current time to the client. And the keyword here is handle time client. And what that does, gets the current time, converts it to a string, and it prints it. And if I just do that on the listener, I get an idea of the kind of output that the time server provides. And the rest is pretty much just configuration. And you see there's very little code to write if you want to implement a TCP/IP server. There's a library that handles all the mechanics of starting new threads, logging connections, listening on the socket. All you have to do is say, I want a server, it has this name, it listens on this port number, and when a client connects, it runs this quotation. And by the way, here I'm listening on a standard insecure port, but if you want to do SSL, you just change 2 characters. So let's start the time server and connect to it with Telnet. And doesn't seem to work. Oh, sorry. Yes, and here's the current time. I just got the port number wrong. It was a typo. Okay. So doing something like this in most other languages, you're looking at a page of code, unless you use twisted Python, for example. So what we have is similar to that, but it's built into the I/O library. It's not a third-party project. Here's another example. This is a web application. And it's a really simple web application. All it does is it gets the IP address of the client, and it displays it in the web browser. And again, it's a very short piece of code, and it leverages a lot of existing functionalities, such as the HTTP server and the web framework. Let's start the web application. I forgot to write a little bit of code here. There we go. now when I connect to localhost 8888, it tells me what is my IP address. Okay, and this is not very interesting. If someone had connected from a remote machine, it would actually show their real IP address. And I guess it's interesting that it's using IPv6 and not IPv4. Sorry?
That should be colon 1, right?
Yeah, the question was, shouldn't that be colon 1? Well, colon 1 is just IPv6 shorthand for the same thing with lots of zeros, okay? So this web application, it's not, whoops, it's not as fancy as it could be. And it has one other file, which is an XML file. And this is just the HTML template where this part is the dynamic content that gets inserted. So our web framework separates the markup from the logic, and it always produces well-formed XHTML. And it supports a lot more features, which I'm not going to have time for today, such as SSL and session management, and basically everything you would expect in a web framework. Okay, the next example, it's a client for the Yahoo Search web service, and I would use Google Search, except you guys don't have a public API anymore. And the main word here is search Yahoo, and this is very typical stack code. It looks like a pipeline where you construct something, you perform an HTTP query, you parse the XML, and then you do more processing on it. So let me do a Yahoo search. The input is a search object, and I can search for factor. Use Yahoo. Oops. Okay, the search word takes the query as a parameter. My bad. Okay, there's a Yahoo search, and the result is like a sequence of tuples. This is the right one. See, we're number 1 on Google, but only number 9 on Yahoo.
They have an attribute with results rubbish. So.
Yeah, and this example, it demonstrates the XML parser, because when Yahoo gives you the search results, you get a string with XML in it, and then you parse it, and now you get an XML object. But to get that nice sequence of results, you have to do some more processing. And we have all kinds of XML APIs for that. Okay, here's a pretty cool example. It's a simple web browser, and it uses the Cocoa binding that we have to call the WebKit API. And again, this is extending the factor syntax for a domain-specific task, and that is interacting with Cocoa. I'm not going to talk about the syntax here because I'm running out of time, but basically we create instances of Objective-C classes, we send messages to them, we load Objective-C frameworks, and this is all done with factor code. And furthermore, I'll demonstrate the deployment tool. You're not always limited to running your code inside the factor environment. You can actually generate standalone executables. So I'm going to deploy here.
How big is the result?
We'll see. The question was, how big is the result? And it's actually it's 764 kilobytes. Let's run it first, and then we'll look inside the package. Okay, I just did this as a joke, live search. And with live search, I think it's even worse. If you search for factor, then, well, the Wikipedia page is number 4, but the main factor website is not even in the first page of results. Oh, there, right there, yeah. Okay, so Google has the best search placement for my project. And if you look inside the executable that was generated by this deploy tool, I lost the original file, so I'm going to just deploy it again instead of searching for it. Okay, show package contents. This is a factor virtual machine, and it's 176 kilobytes. It's pretty small. This is the main launcher executable, and that's even smaller. And the only substantial content here is the image file, which contains serialized factor data as well as compiled machine code, and that's 572 kilobytes, which is a fair bit for a trivial application of one page of code. But you have to consider that this is a very high-level, very dynamic language with garbage collection and so on. And it's also a 64-bit binary. I'm running factor in 64-bit mode here. So that's pretty good. If you look at Lisp systems out there, then they'll give you a 20 megabyte binary for a hello world. And other languages such as Java, they don't even generate standalone binaries. You have to ship the Java VM, which can be quite large. So the deploy tool is pretty neat. I'm going to skip this example, and I'll just talk about the implementation now. So factor, mostly it's written in itself, but there is a part of factor in C, and that's pretty much the garbage collector and other low-level services like that. The core library is 9,000 lines of factor, and that includes arrays, hash tables, the parser, the object system, stuff like that. And we also have the basis library, and that is other libraries which are pretty much essential these days, but they're not fundamental to the language itself. This includes parsing XML, the GUI toolkit that I'm using here, local variables, the web framework, stuff like that. And factor is fully compiled. There's no interpreter. Even when you type stuff in the listener here, it becomes machine code. So I type 22+, and it actually compiles it very quickly and runs it. And I don't know if I have time to go into the compiler. I mean, how are we doing for time? 5 minutes? Okay, well, I'll just give you a very quick tour of the compiler. I have this benchmark here. And this benchmark renders a fractal. So let's run it. Press Control-T. 330 milliseconds. Okay, that's the output. And this benchmark here uses all kinds of crazy language features, such as complex numbers, and all the arithmetic in factor is generic, meaning that in theory there's runtime dispatch on the types. It constructs quotations on the fly, for example, but it's very fast. And see, when I did open there, it tried to open OpenOffice. And it's very fast because the compiler performs a lot of advanced optimizations. It eliminates memory allocation, and it eliminates runtime dispatch, and it eliminates redundancy in the low-level code. And basically, the way it's implemented is it converts your factor code into something called SSA, single static assignment form. And the idea with single static assignment is that every value has a unique internal name. And this lets you implement all kinds of optimizations very easily. there's a high-level optimizer with 12 different passes. And let's see. I'm just going through this very quickly because there's no time. We infer types. We infer the ranges of values, lengths of arrays if they're known. It does some constraint analysis where, for example, you can have a piece of code like this where you're saying, is the top of the stack an array? And if so, give me the first element. And it knows that inside this quotation, you have an array on the stack because the only way the result of this could be true is if you had an array on the stack. And if the optimized dot word tells you how a piece of code is going to be compiled approximately. And in this case, you can see all this crazy stuff got inlined and expanded. And these are all low-level primitives, which will map directly to machine code. So in the Mandelbrot benchmark, it eliminates a lot of the generic dispatch in this pass. The next pass is called escape analysis. And here we identify tuples which are allocated inside a word but are never returned from that word. And there are a lot of these tuples in Factor because we encourage a high-level programming style with rich data types. And being able to eliminate these allocations really helps with performance. For example, complex numbers are represented as tuples of two components. But if you can eliminate that allocation, then your complex number arithmetic will be a lot faster. Another example where tuples can be eliminated is virtual sequences. For example, if you want to iterate a sequence backwards, then you can wrap it inside a reversed sequence. And this is called a virtual sequence because the length and nth methods on this sequence will delegate to the underlying sequence, but they'll present the elements in a reversed way. So here it's 3, 2, 1. But it would be annoying if every time you called reversed and then did each on it, it would allocate a new object of the reverse type. Because here it's not being returned or anything, and we're not holding an instance of it. We're just creating it, using it, and then discarding it. And in fact, the optimizer, when it inlines everything and expands everything out, there's no allocation here. And after type inference and escape analysis, it just cleans up the code a little, eliminates some unused generality branches where the condition is now a constant Boolean. Okay, and the next step is it converts your code into register-based code. And at first it does this in a very naive way. For example, stack operations will always expand into memory writes. So if you're pushing 5 on the stack, then the compiler loads 5 in a register and stores it on the stack. Or if you have a swap in your code which swaps stack elements, then it becomes 2 memory reads and 2 memory writes. If you just have calls to words, then they're just calls. But once it expands your code into this register form, it does further optimization. And some of these are quite advanced. For example, this word toArray, it makes an array with the top 2 stack elements. And if you look at the definition, it's very general. There's a lot of generic dispatch going on. And the high-level optimizer gets rid of the generic dispatch, but there's still a lot of redundancy because the inlining gives you stack shuffles, and the semantics of the array constructor are such that you have to fill in the array with the initial element, but then you're overriding all the elements anyway, so there's redundancy there. But the low-level optimizer eliminates all that redundancy, and the machine code that's generated for this constructor is pretty much as optimal as possible. There's no stack operations at all except for loading the 2 inputs. It also does something called value numbering, which identifies redundant computations along the same control flow path. And in the case of Mandelbrot, for example, there's a lot of boxing and unboxing of floating point values where, because of the dynamic typing in Factor, you have to do a memory allocation for each floating point number. But if you can prove that all values are floating point numbers, you can eliminate the boxing, and that's what value numbering does. And again, there's some dead code elimination to clean it up. And the last step is register allocation, where the intermediate form used by the compiler assumes you have an infinite number of registers, but in a real CPU, you only have finitely many. And in general, it's a hard problem to allocate the registers optimally. But we use a relatively decent algorithm called linear scan. And I'm going to skip the details here. So in the end, if you look at the inner loop of the Mandelbrot benchmark, it's very tight. You have just floating point operations, and these run as fast as your CPU will allow. Okay, the garbage collector is pretty good as well. It's a generational collector, which means that short-lived objects, even though those which are not eliminated by the compiler, they're still very cheap to allocate and deallocate. And it's also precise, which means that it can always differentiate a pointer from an integer, which is not the case in some language implementations. And the next thing is that our project infrastructure, like all the websites that we have, like factorcode.org and our wiki, they're all written in Factor, and they use our web framework. And we also have a build farm which compiles Factor on 12 platforms. So you can see we support 3 different CPU architectures and a range of operating systems. And all of these binaries, they get generated every time somebody pushes a patch and all the tests pass. So if you push a patch and something breaks, then you get an email. But if all the tests pass, there's a new binary. So we don't have to make releases. Of course, we do have to make sure that test coverage is very good. But in general, this works really well. And finally, the Factor community, mostly people hang out on the IRC channel and the mailing list. And both are pretty active. And a number of people have also contributed code to Factor. There's about 30 people that have contributed code to Factor itself. And more people have used Factor for their personal projects. And it's easy to learn. There's a lot of documentation. If you look at the documentation in the environment, there's a cookbook and a tutorial, and they go through things very slowly, much more slowly and in a lot more detail than I've been doing in this talk, because I really wanted to demonstrate some more advanced features. And finally, I'll talk about the future direction. We haven't released 1.0 yet, but we will at some point in the near future. And for 1.0, basically, we'll be doing what we've been doing with polishing the language and always improving the stability and the performance. And then 2.0, that's going to be a release where we rewrite everything for concurrency and native threading. And we also want to have a syntax-aware Factor editor. And finally, we want to explore embedded programming and using Factor as a scripting language inside other applications. So this is maybe a year or 2 away. And that's it. Again, it's hard to cover everything in a single talk because there's just so much in Factor. And also, it's hard to find a balance between going through all the language features in great detail and giving many examples. But I hope that I've generated some interest, and maybe you'll want to check out Factor, and I encourage you to do so. Any questions? Yes.
What's the stability of the core language?
The question was, what's the stability of the core language? So there's 2 forms of stability. There's stability in terms of how quickly is the language changing, and also stability as far as crashes and stuff like that. So the first form of stability, the language, we're still tweaking things here and there. And last year was a period of many language changes. This year we've made some changes, but lately it seems to be stabilizing, and we finally have something we're pretty much happy with. And anybody who contributes code to the Factor repository will refactor that code if the language changes. If people have their own Factor code, then they'll need to stay up to date, because every once in a while the core language does change, but it's becoming more and more rare now. Mostly now it's just API changes in the more peripheral libraries, and even those are starting to stabilize. And as far as bugs and crashes, well, it didn't crash during my presentation, and in general, it's very stable because of our continuous integration and our build farm, which runs tests all the time. I have websites running on Factor, and they've been running nonstop for months on end. I mean, the last time I remember restarting the Factor HTTP server was actually a problem with the Linux that was running the website and not Factor itself. So it's very robust and very stable in that regard. Yes?
Where do you see Factor as sort of finding its happiest home in terms of application domains or types of problems?
Okay, so the question was, what types of problems and application domains do I see being Factor's happy home, so to say? Right now, our main focus has been on developer productivity, which means we want to design a language that people can write a lot of code in very quickly, and a language which doesn't get in your way, a language which you can extend, a language with a robust implementation. So any kind of general purpose programming task, I think, is a good fit for Factor. But we're always on the lookout for problem domains where it's a really good fit. And I think so far, the most interesting one has been just anything where you need to extend the syntax to express your problem. For example, writing parsers with pegs is a really nice Factor application. And yeah, we have a set of features that very few other languages have, because we have a dynamic language, but it can also generate standalone executables, and it's very fast. Last time I did some benchmarks, I think it was about 50 times faster than Python on floating point code. So it's almost as fast as C on many things. And we also have very flexible language features that you would find in Lisp and Scheme, for example. But on the other hand, we also have a lot of libraries and a robust implementation. So it's not just a research language, it's something that can be used for production. Yes?
Have you developed any means of collaborating or working as a team? Because I've heard the criticism made of high productivity complex or compact languages that they're write only for a single person, and handing over code is an issue.
Okay, so the question was that have we had any problems working as a team with a language that's as extensible as Factor? And the questioner commented that such languages have a reputation for being write-only. See, I think when you're looking at a piece of code in any language, sometimes it can be hard to figure out what the code is doing if you're not familiar with the problem domain and the algorithms used in the code. But the nice thing about Factor is that it has very powerful code browsing capabilities. For example, I can type the name of a word, and I can say, hey, Factor, who calls this word? And it tells me that all these words use the append word, for example. Or you can look at the definition of a word, and then you can see what its definition is without having to, like hunt around for it in your text editor. You can click on a word that it calls and read about that word. You can right-click on something and look for usages. So I think the way to make a language that's useful for team programming is to make it easy to explore the code base using tools in the language. And also have just, you need coding conventions, of course, but tools are the major solution to that, I think.
Thank you.
Yes?
What does the backslash word do?
What does the backslash word do? That's a good question. Backslash is a parsing word which reads the next word that you type, but instead of executing it, like if I just say plus, that executes plus, right? If I say backslash plus, it puts backslash on the stack, so you're just escaping a word, sort of. So for example, I can say backslash plus edit, and then it opens the plus word in my text editor, and this is where it's defined. This is like a file in core math. And backslash, that's a word as well. Like I can say backslash C, and it shows me the definition of backslash. Any more questions? Okay. Well, thank you very much.